Welcome back to everyone, and welcome back to Hannes Herrmann, who's here to talk to me about quantum computing, and also to everyone else as well. And I'm David Cooper, of course. So, Hannes, what's your prepared 30-second overview of what a quantum computer is?
Quantum computer is like a normal computer, but rather than using bits, it uses qubits, which means it has access to additional power through quantum entanglement.
Yeah.
That effectively gives it some additional oomph, and the problem really is to decide just how much of that oomph is actually real.
So what does real mean in this case?
Well, first of all, there's the practice of what's happening with quantum computers, because actually building a quantum computer and letting it be stable for more than like half a minute is a very challenging thing. Then there's, assuming we had this wonderful computer that was stable and whatever, what could it actually do? And the way that this is communicated, especially to funding agents and to the public, whatever, by the media, including academics, is not necessarily what it's actually going to do according to the mathematical models behind it.
Indeed, I actually was watching a YouTube video about this last night, and there certainly seems to be a few myths about the power of quantum computing, and the idea that, probably based on how it's usually described, where people think that it can just do all of the classical computations in parallel and then you get the magic answer at the end.
Yes.
So is there an easy way to describe what it's doing instead of that?
Yes, there is an easy way to describe it. The power of a quantum computer can be summarized as being the set BQP.
Okay.
Which is the set of bounded error quantum polynomial time algorithms.
Oh, thank goodness for that.
But you have to understand a bit more about computability theory to understand what that actually means. I can summarize if you like.
Yeah.
The general idea is that it's computer science, right?
Yeah.
And it's a field of mathematics, so what we do is we try to mathematically model things so we can say this is actually what's going to happen.
Yeah.
And when we do that, our computers turn into Turing machines. And most people would have heard of Alan Turing, of course, and Turing machines are the mathematical model behind the computer, and we can say what can and can't be computed and how efficiently using that model.
Yeah. So all current computers are often thought of as being Turing machines.
All the von Neumann architecture, yes, absolutely.
Yeah, okay.
There are other computers such as built out of leech brains and whatever that aren't, but the normal, what we consider normal computers, yes. Yeah. And that's nice, but when we do that to quantum computers, it shows that quantum computers probably don't even have an overlap with the set of intractable problems. So when we mathematically model our normal problems, we get this large set called NP, which contains most of the decision problems that we normally look at. So decision problems being yes, no answer, because that's a mathematical model we use. And there's a set in there called P, which are all the easier problems, the ones that we can solve fairly easily.
Yeah.
And there's a set called NPC, which is the ones that are going to be harder. And if we can solve even one of those in an easy way, then the whole thing collapses. We can solve all of them easily.
Yeah.
So that's called the P versus NP problem, and that's one of the Millennium Prizes, of course. If someone solves that, there's $1 million US, fame, eternal fortune, that sort of thing.
Feels like it's probably worth more than $1 million, but still.
Well, there's $1 million sitting there just that, but I mean, you get that. You get a professorship at the university of your choice. You've got your life set basically, which is nice. And it's, one day some student is going to do it. It won't be an academic, just like normal.
Yeah.
And the prevailing view at the moment is that P is not equal to NP.
Interesting. Okay.
I personally still hold out some hope, but the prevailing view is P is not equal to NP. So no, we're not going to force it to collapse. But if we can show that's not equal to NP, then that will at least tell us something.
Still very interesting, yeah.
Oh, absolutely. It's a interesting problem thing. So, when you look at the set P, that's the problems that can be solved in polynomial time on a deterministic Turing machine. There's also a set called P space, which is the set of problems that can be solved in polynomial space in a deterministic Turing machine, which is much larger than actually P.
Okay. Yeah.
And what we can show is that the set of problems that can be shown by a deterministic, a quantum Turing machine, is a subset, possibly a proper subset, of P space.
Okay. So, but not P exactly.
Not P, but P is actually a subset of BQP. So that P, anything that's currently solvable in Polynomial time can be solved in Polynomial time on a quantum Turing machine. That's not a problem.
Yeah.
The problem is the advertising is saying things like, oh yes, you can solve all this encryption stuff on a Turing machine.
Yeah.
When that's not necessarily the case. I mean, some of them, yes, we've got algorithms that can do some of them. There's a whole war going on in encryption, quantum encryption, quantum safe encryption stuff, which is also lots of fun. But even if they break all of if they manage to solve all of the physical problems with building a quantum computer, you still have this problem that people tend to believe that they're going to get this marvelous thing, which is effectively a non-deterministic Turing machine, but actually isn't, according to the theory.
Yeah, they think that it's going to be an oracle machine where the idea that it can just solve things instantly.
Yeah, so for the listeners who might not be aware of what we're talking about, the idea is, imagine a computer where you could say, do all of these things at once. So check all these different possibilities at the same time, and then if any one of them works, give me that one. Yeah. That's the non-deterministic Turing machine version, and that's what people are talking about with quantum computers. But of course, that's not the case.
Yeah.
Having said that, quantum computers do have some strengths. For example, quantum annealing is commercially viable, has been for years now, and has solved some very interesting problems, protein folding, for example. Yeah. So that part, the optimization, quantum computing is really good at that. But that's a subset. Yeah. That's not a general quantum computer.
Right. So ultimately what we're going to have is something that is potentially useful in certain cases, but is not the power of the gods.
Yes, essentially. Having said that, when you go back to the theory, there was a gentleman, I think it was called Deutsch, who proposed a adjusted model of a quantum Turing machine. Incidentally, the quantum Turing machine has an interesting property that it can be, you can undo anything you do. So when you run instructions, you can step back those instructions at any point to get to any previous time. And that paper also then shows how to do that for normal quantum computers. So people building quantum computers, that would be part of the properties that people aren't aware of, which is sort of cool, right?
Yeah.
But the more important thing is there's this thing called post-selection. If we can modify the likelihoods of certain quantum states occurring, because the quantum computing isn't really probability based when you get right down to it, because probability is something associated with ignorance. Whereas with quantum computing is there's a chance of this, a chance of this, but it has happened or it will happen, and it's not like we can't see the coin basically. With post selection, if there's a way we can affect which way things are going to turn out in any way, and add that to the machine, then the quantum Turing machine with post selection becomes equal to the non-deterministic Turing machine.
Oh, okay. What is post-selection then?
So that's affecting, you know how quantum computing works, right? When you look at a qubit, when you're looking at a normal bit, there's one way to read it. When you're looking at a qubit, there's two ways to read it. There's door A and door B, effectively.
Okay, yeah.
And if you open door A, you get one answer.
Yeah.
If you open door B, you get another answer. But if you open one, you can't do the other anymore. And you'll never know what would have happened if you got the other. Yeah. If we can modify our knowledge of that to some extent, then that helps us effectively make more informed decisions of what we're doing with the when we're asking the quantum computer questions, and all the checking out all the entangled solutions and things.
Yeah.
So that's a rough overview of post selection. Now the thing is, post selection, as far as I'm aware, no one's actually investigated whether it's actually possible. I haven't met anyone who thinks it's possible. But there is a theoretical model that would give us all the wonderful things people are saying, but no one's, as far as I know, investigating it.
There's always more problems on the horizon, I guess. That's otherwise life would be very boring, wouldn't it?
There is, yes. But Australia is doing some great work in quantum computing, both from the hardware side. There's a lot of good hardware work being done over east, especially because trying to keep, once you've got the qubits set up, trying to keep them from what's called decoherence.
Yeah.
So if the information going away is very hard.
Seems to be it's the major hardware problem, I think, isn't it?
Yes, it is. Which is why normally when we build a quantum computer with like 200 qubits, we only use 100 of them to use the other 100 for error checking, effectively.
Yeah.
Which is not efficient, but it's about the best thing we can do.
So there is like some of that solving that problem kind of eats into the benefits that quantum computing would otherwise have, presumably.
Oh yeah, absolutely. But I mean, if we can find better materials, and that is improving all the time, if we can find better ways of doing error checking algorithms, which is also advancing, things are moving forward really rapidly. Lots of governments and organizations are throwing money at quantum computing.
Yeah.
Certainly there's a few other interesting spin-offs like quantum communication, which China is quite advanced in at the moment.
Yeah. So that quantum cryptography in particular, that's
okay, so there's two types of quantum cryptography.
Yeah.
First of all, there's the algorithms, which are trying to encrypt things using quantum computers and decrypt things using quantum computers.
Yeah.
Then there's the actual, I guess, what people call quantum cryptography, but it's not really cryptography. The thing with quantum computing is, if you've got two qubits entangled, and you look at one of them, then the state collapses. The other bit immediately knows. So if you're using qubits that are entangled, but an entanglement doesn't necessarily have a distance limit, to communicate in some way, and somebody peeks in on that communication in any way, shape or form, everyone immediately knows about it.
So it's a physical layer thing.
Yes, it's effectively a physical communication thing. Now, how that works practically, hard to say, but quantum communication satellites have been going up for some years now. Even a couple of small quantum CubeSats have gone up. A person I know in the UK put one of those up, actually, and there's his IEEE videos on my site, I think. But there's a lot of work being done. A lot of it is not necessarily being advertised as widely as it could be because it's not the big shining quantum can do everything.
Yeah, it's trying to find your way through the mazes. You've got the hype merchants on one hand, but there's still some real work to be done on the other hand, and I can see there's a tension there, isn't there, I guess?
There is. Obviously, people want to get funding for their pet projects, and the more hype you have, the better.
Yeah.
Some of the hype is truly ridiculous, but there it is. There's a lovely video from back when YouTube and a few other big companies paid huge amounts of money for one of the first D-Wave quantum computers. So it's a quantum annealing computer. That's now maybe 8 years ago or so. And what they were saying about it was, amazing! It could solve problems faster than all of Google's data centers put together and stuff.
Of course it can.
Yeah, nah. Especially because it's a simulated annealing computer. It's not a general computer.
Yeah.
But that hype is huge, and that's a problem because it means the people who are doing actual work are going to find it hard to get funding. It's like, I want to do this with quantum computing, which is actually realistic. Yeah, but these people are promising the world,
That's and so you force everyone to go down the hype path that way, I
guess. To some degree, yes. Yeah. And of course, then you get to quantum supremacy, which is another fun toy, which Google has been playing in as well. So. Yeah. For those who don't know, quantum supremacy is when a general quantum computer can solve a problem that is considered too intractable to be reasonably solved on a non-quantum computer. And as far as I'm aware, every claim of quantum supremacy so far has been quickly matched by a existing non-quantum computer being able to do the same thing, because normally the quantum supremacy was actually advanced in an algorithm which can translate to an algorithm in the normal computers.
Yeah,
so
interesting dynamic.
They go, "Oh, we've thought of this really great thing to do this really well, and we did this on our quantum computer. Yeah, but so we can do it maybe not quite as well, but because the modern computers have so many more bits, it's you're working with a couple of hundred qubits versus tens of thousands of bits.
We've spent
millions, of course,
decades upon decades refining the way that normal computers work.
Absolutely, yes. So quantum supremacy isn't here yet, but as far as I'm aware, but the quantum computing is very powerful, and there's many things it's really, really good at. And the real problem we face is that once we find a killer quantum application, we're not going to have the coders for it, because no one is really teaching quantum computing.
So, how do you teach quantum computing?
Well, I've actually been talking to the school about setting up a minor specialization in quantum computing. That would be a little difficult, though. Quantum computing does require you to understand the basics of quantum physics in order for you to do it properly. Not all of it, but you need to know at least how the qubits work and that sort of thing. So it's fairly mathematical, and it is a fair bit of work. The good news is anyone who's interested in trying it can just go and, for example, you want to go and download Q Sharp, Microsoft Q Sharp, and just download it, and that's a simulation. But a lot of the companies that have quantum computers, they will let people effectively use their quantum computers free. Like D-Wave, they've got this website. You can go on there, you can put your program in, and go into a queue, and eventually they'll run it for you, essentially, and tell you the results.
Very old school.
Because they want to advertise their services, they want people to practice using quantum computers. And of course now our Pawsey also has a deal with a quantum computer. So our students and staff can also use quantum computing, but again, they'll have to apply for it just like with the rest of the Pawsey machines.
So we have to build up some expertise around designing algorithms, because from what I understand, the current, in order to build a quantum algorithm, it's a matter of jamming together a whole bunch of quantum gates, and I don't think we have. I certainly don't have the intuition for how you put together a whole bunch of quantum gates to make something useful happen. Obviously, you can, but it's a tricky issue.
I would say it's a bigger jump than going from procedural to object-oriented computing, because not only do you have to change your way you think, but you also have to understand that really tricky concept.
Yes.
Whereas with OO, the concept is something that's already native to us.
Yeah.
So it's a really hard barrier to entry. And I've always said, hey, sometimes I'll take 2 to 3 months to just figure this out. But of course, no one has 2 to 3 months spare, right? So
yes, that's a luxury.
yes, indeed.
Yeah. What do you think the timeline is going to be? Just out of reading the tea leaves, as it were.
A couple of years, the last lecture of TFCS every year is other computing models, and a large part of course, quantum computing. A couple of years ago, I said, look, quantum computing is going to really start making some big differences soon. And it turned out a few months before that, it had actually done, I just hadn't noticed that. Yeah. So there are real advances being made, for example, with the D-Wave quantum annealing. General quantum computers haven't done an awful lot. Like I said, there's been things that they've done, but they've then been able to be replicated on more general machines. But that discussion on just trying to do it on a quantum computer, it does make people think differently, and then that has translated to the normal machines, which is sort of nice.
Also good, yeah.
There's enough happening just with the simulated annealers, the quantum annealers, that I would say quantum has already been shown to be worthwhile in that very narrow area. General quantum computers, that's going to wait a while longer. That's probably going to need to be a hardware thing rather than a software thing. But still, the amount of, for example, quantum encryption, the amount of work going on there is already quite large. And while I don't understand what's going on with quantum computing, there's enough people throwing up satellites that I'm assuming something's happening there. That we're not really being told about too much, but I don't know.
Yeah.
Maybe I'm not less interested in the hardware, so I haven't really paid much attention. But yes,
hardware. Who needs hardware when you've got software?
yes.
I might leave it there if that's right.
Yeah, no
so, thank you so much for that. That's been really informative. And there's lots of other resources that people can access about quantum computing, of course, as well.
And I should add that, I mean, I am a theoretical computer scientist, so from the theoretical models I do have an understanding, but I'm not an expert in quantum computing. So all of this is the research that's freely available, and I just want to make it clear that I don't want to sell myself as an expert in a field that I'm not an expert in, really.
Fair disclaimer, yeah. But thank you for your contribution. So
thank you, Dave.